Well, here we're asked to find the x and y intercepts of our polynomial here, p of x, which is equal to x times x plus 7 times x minus 6 squared. We're going to start off looking at the y-intercept. That is typically a little bit easier to deal with, so we're going to replace the p of x with our y, and then put a 0 in for x, and we're going to solve. So we have 0 times 0 plus 7 times 0 minus 6, quantity squared. So this leaves us with 0 times 7 times 36. The rest of this doesn't matter because we're multiplying times 0. That means everything here is going to be equal to 0. So that's our y-intercept. Now if they're asking you to write this as an ordered pair, that'll be the point 0, 0. You know, the first 0 from the 0 we put in for the x, and we found y to be equal to 0. Now for our x-intercept, we're going to do similar sort of approach here, and we're going to take and put a 0 in for y and solve for x. So we have 0 equals x times x plus 7 times x minus 6 squared. Since this is already in factored form, we're just going to take and set each factor that has an x in it equal to 0. So we have x equals 0, x plus 7 equals 0, and x minus 6, quantity squared, is equal to 0. Now in the first one, x is already equal to 0, so we're done. So this is one x-intercept. For the second, we're just going to take and subtract 7 from both sides, so that gives us x is equal to negative 7. For the third, we have x minus 6 quantity squared, but that's just x minus 6 twice, so really we just have to figure out what happens when x minus 6 is equal to 0. So we'll add 6 to both sides and get x is equal to positive 6. So there's our three x-intercepts. If you're asked to write them as an ordered pair, remember we had y equal to 0, so we have the point 0, 0, negative 7, 0. So we have the point 0, 0, the point negative 7, 0, and the point 6, 0 for our x-intercepts. Alright, here we've been asked to find the x and y intercepts of a rational function here, r of x, which is equal to x minus 3 times x plus 3 in the numerator over x minus 4 times x plus 1 squared in our denominator. First, we're going to start off with the y-intercept, as it's usually a bit faster, so we replace the r of x with a y, and then put a 0 in for x, so that'll leave us with negative 3 times 3 over negative 4 times 1 squared. And it's just a matter of working the rest of this out, so we have negative 3 times 3, which is negative 9, over negative 4 times 1 squared, which is 1 squared is 1, so times negative 4 is negative 4. So this gives us our y-intercept at positive 9/4. And if you're asked to write this as an ordered pair for the y-intercept, we put a 0 in for x, and we found the y value to be 9/4. For the x-intercepts, now we put a 0 in for y, and we solve for x. So we have an x minus 3 in the top, times an x plus 3, over x minus 4 times x plus 1 squared. Now for rational functions, finding an x-intercept can be kind of irritating. It's because there is a set of variables in the top and also ones in the bottom of the fraction, so that can be a bit confusing. Now the good news is we're going to be able to get rid of the denominator entirely, because we're going to just treat this algebraically and multiply both sides by the denominator in order to get rid of them. So we'll take and multiply both sides by x minus 4 times that x plus 1 squared. Now on the left side, these things are being multiplied times 0, so what's going to happen when we multiply times 0 is it stays a 0 here, and for the right side our x minus 4's cancel out, as do our x plus 1 quantity squareds. And so life is much simpler. So we're left with x minus 3 times x plus 3. At this point, we're in a factored form, just the way we'd like it. So we're going to take and set each of these two factors equal to 0. For the first one, when x minus 3 is equal to 0, we just add 3 to both sides. So we get x equals 3. For the second, x plus 3, we subtract 3 from both sides and discover x equals negative 3. So these are our two x-intercepts. If we're asked to write these as ordered pairs, these would be the point 3, 0, because the x value we found for 3, and we put a 0 in for y, and negative 3, 0, for much the same reason. So there are our x and y intercepts for little r of x. We're given the function p of x equals x times x plus 7 times x minus 6 squared. So this polynomial has a number of features we can look for. If we're going to find the y-intercept, we just take and put a 0 in for x. So we'll substitute a y in for p of x, and we have 0 times 0 plus 7 is 7. 0 minus 6 will be a negative 6 squared. The rest of the multiplication is pretty much done for us since we're multiplying everything by 0 in the end. That gives us a y-intercept of 0. If we're going to write this as an ordered pair, we would write it as the point 0, 0. Now for the x-intercept, I'm going to reverse the process. So we put a 0 in for y, and then solve for x. So we have x times x plus 7 times x minus 6 quantity squared is equal to 0. Since this is already equal to 0, all we have left to do is take each factor that has a variable in it and set it equal to 0. So we have x equals 0, x plus 7 equals 0, and x minus 6 squared is equal to 0. Now with the x is equal to 0, we're already done. Here for the x plus 7, we just take and subtract 7 from both sides to get x equals a negative 7. For the x minus 6 quantity squared, it doesn't matter if you just look at x minus 6 squared or just the x minus 6. I'll take it as the x minus 6 quantity squared, so we'll square root both sides first to get x minus 6 is equal to 0. Then we add 6 to both sides to get x equals 6. We can also find the multiplicity of each root. And so if we're going to do that, what we will have to do is just examine the exponent on each of the factors. Alright, so to find the multiplicity of each 0, or root, we just take and look at the exponent that led to us getting that. So we had zeros at x equals 0, at x equals negative 7, and at x equals positive 6. Right, for x equals 0, that factor that gave us this was x. And since there's no exponent explicitly listed here, we assume that to be the first power. So for x equals 0, this guy has a multiplicity of 1. For x equals negative 7, that came out of this x plus 7, and again, it's also assumed to have an exponent of 1, so his multiplicity is also 1. And for the x equals 6, that came out here of the x minus 6 quantity squared. The exponent there is a 2, so for the 6, this guy has a multiplicity of 2. Now the multiplicities are important mostly so we can determine how the graph behaves at each of these zeros. So if it's an odd multiplicity, it's going to cross through the x-axis at that 0. If it's even multiplicity, it's just going to touch. Now we can also find the degree of this function, and since we have this in factored form, in order to find the degree, all we have to do is add up the respective multiplicities. So we have here 1 plus 1 plus 2, which tells us our degree is 4. The degree helps us here in determining the end behavior of our polynomial. If it's an odd versus an even number, just like with multiplicity, it has an effect on the shape of the graph. And then lastly, we can find our leading coefficient. And that's simply going to help us determine which way the graph is going to follow its degree. Right now, the leading coefficient is most easily found if we have our polynomial in a completely multiplied out form. Well, since we don't have that here, we have a little bit of extra work to do, but it's not too bad. So we just look back here at our original polynomial, p of x equals x, the x times x plus 7 times x minus 6 quantity squared. And we say, okay, if I were to multiply out the x minus 6 quantity squared, that would give me an x squared plus some other stuff. Now, I don't care what that other stuff is. I care about just the biggest degreed thing in that particular factor. In this case, that would be an x squared. Now we're going to multiply that guy times what's going to be the only part we care about here in the x plus 7, which is the x. All right, so the x squared times x, these two guys multiplied together will give us an x cubed plus 7x squared and a bunch of other things, so I don't care about those. Oops, forgot to drop the x down here. Don't want to leave him out. And then finally we'd multiply all this other stuff out. We would distribute the x through everything that's in the parentheses, and that will give us an x to the 4th plus a bunch of other stuff that we don't care about. Now we already know that the degree is 4, and that's been confirmed here by our work, but it's worth looking at again here. So that would be our exponent in the multiplied out form. But for our leading coefficient, we don't have anything written here, so we're going to assume that to be a positive 1. Right, so now, when we come to look at a graph of all of this, we want to go back through and, again, just briefly mention everything that we found. I'll do this in a reverse order. So we found that our leading coefficient was positive 1. Our degree was 4. Our zeros were 0, negative 7, and positive 6. The 0 of 0 had a multiplicity of 1. Positive 7's multiplicity was also a 1, and the 6 had a multiplicity of 2. We had our and then lastly we had our y-intercept at the point 0, 0. So based on the information we've carried over from all the stuff we found, we're going to try and sketch our graph here. So we'll start off with our y-intercept, which is at the origin. And the good news about the origin is it's both an x and a y-intercept, so that takes care of the 0 at the 0 as well. So now we're going to go ahead and draw in the other x-intercepts. So we have 2, 3, 4, 5, 6, 7. So there's our negative 7. Oops. Went too far there. Also, here's our positive 6. So we'll fill in both those lines here and here. And so now we have our degree of 4. So that's going to tell us our graph is going to either start up and end up, or start down and end down, depending on what our leading coefficient looks like. In this case, our leading coefficient was positive 1. And the fact that it's positive is what makes the difference. So that means we're going to start up and end up here. So we'll get rid of these. In fact, here, let's just draw these in black. So we start up, then we come down to -7. Now, because of the multiplicity of 1, we're going to keep on going through -7. Then we're going to come back up, cross back through the origin at 0, 0. And at some point, we're going to turn around. And then 6, we had an even multiplicity, so we're just going to touch the x-axis there, and then head back up the same side to finish our graph out this way. And so that's our brief and rough sketch of the graph of our polynomial p of x, which equals x times x plus 7 times x minus 6 quantity squared. We've been given the polynomial function capital P of x equals 5x to the 5th minus 50x to the 4th minus 120x cubed. We'll start by looking for the y-intercept of this polynomial. So we'll replace the capital P of x with a y, and we'll put a 0 in for x. So that'll give us 5 times 0 squared, or 0 to the 5th, excuse me, is 0. Minus 50 times 0 to the 4th is also 0. Minus 120 times 0 to the 3rd is also 0. So that tells us we have a y-intercept at 0. Now, if we were looking to put this into an ordered pair, we could take and write this as 0, 0. But for right now, I'm just going to leave this as is. Now, for the x-intercepts, now we take a 0 and put it in for y, and then solve for x, so we get 0 equals 5x to the 5th minus 50x to the 4th minus 120 x cubed. And since this isn't a quadratic, the quadratic formula obviously won't apply here, so let's stop worrying about any kind of fancy formulas and just see if we can maybe factor this guy out. So first step we should do in any factorization is look for a greatest common factor. So you have 0 equals, and everything in it has at least a 5, and they'll have x's, so the biggest we could pull out is the smallest power of x, which would be x to the 3rd. So that leaves us with an x squared minus 10x minus 24. Now, before we jump into solving this any further, let's see what else we can factor. Hopefully this x squared minus 10x minus 24 can be factored. Let's see, so we know we're going to have an x in both places. The 24 is negative, so that means we'll have one sign that's positive and one that's negative, or coefficients. And for factors of 24, let's see, we've got 6 and 4. That'll give us 10, as will 12 and 2. And let's see, so we need this to be negative, so that's going to be the 12 and 2. So we'll have a positive 2 and a negative 12. Then the entire factored form would be 5x cubed times x plus 2 times x minus 12. And since we're now in a completely factored form with everything set equal to 0, we can just take and set each factor equal to 0. So we have 5x cubed equals 0, x plus 2 equals 0, and the x minus 12 equals 0. Alright, for the 5x cubed being equal to 0, we divide out both sides by 5 to discover x cubed equals 0, cube root both sides, and we get x is equal to 0. For the x plus 2 equal to 0, we'll subtract 2 from both sides to get x equals negative 2. And for the x minus 12 equal to 0, we add 12 to both sides to get x equals 12. All right, so that takes care of the x-intercepts, or what's called the zeros. Now what we're going to do is look for the multiplicity of each 0. Right, so for the multiplicity, we're going to take and examine what the exponents were on each of the factors that generated these 3 zeros. Right, so with the x equals 0, that came out of our 5x cubed, and so the exponent here was 3. So for the x equals 0, he had a multiplicity of 3. For the x equals negative 2, that came out of the x plus 2. So we're going to look at the exponent here, which is assumed to be a 1 since there's nothing else written. So our multiplicity of negative 2 is 1. And then last but not least here for the positive 12, that came out of the x minus 12, and he's also assumed to have an exponent of 1 on that factor. So our multiplicity for the x equals 12 is also a positive 1. And remember, the multiplicities are here to help us determine how the graph behaves at each of the zeros. Next, we're going to look for the degree of our polynomial here. And since this guy started off in a multiplied out form, we just have to go back to that form and find the biggest exponent on a variable, which in this case is 5. And we can verify also that our multiplicity work came through correctly by adding them up, and sure enough, 3 plus 1 is also going to give us a 5. All right, so we've got our degree both ways there. And then we want to look at the sign of our leading coefficient to help us determine how the graph starts and ends based on the degree. And in this case, since we already have this thing in a multiplied out form, we know our leading coefficient is the number in front of the term that gave us the degree. So that was our x to the 5th, and the number in front of that was 5. So now we're going to take all of that information and I'm going to make little side notes here just so we can refer back to it for the purposes of our graphing. So we had our y-intercept at 0, 0. Right, our zeros are x-intercepts. We had at 0, negative 2, and positive 12. And they had corresponding multiplicities. For the 0, its multiplicity was 3. For negative 2, its multiplicity was positive 1. And for 12, its multiplicity is also positive 1. We determined the degree of our polynomial capital P of x was 5, and that its leading coefficient was positive. With all that information we found, that allows us to draw our x and y axes and sketch out a rough version of our graph. So we'll start off with our y-intercept at 0, 0, the origin. And the origin is not only a y-intercept but also an x, so that's kind of taking care of two birds with one stone. Right. Now rather than make a bunch of hash marks here, we'll just say that this guy out here to the right is our positive 12, and back here to the left on that x-axis, that's our negative 2. And those are the other two x-intercepts in addition to 0. So we'll fill them in like so. Now, based on our degree of 5, And that's an odd number, so we're either going to start down and end up, or we will start up here and end down towards negative infinity, with our leading coefficient being a positive number. That tells us we are going to start down and end up here. So as we're going through, starting here, then we look at negative 2. As we approach, had an odd multiplicity, so we cross through the x-axis there. Then we turn around and head towards 0. Also had an odd multiplicity, so we're going to cross through there as well. And then towards 12, another odd multiplicity, so we cross through it again. And that's our rough sketch of our graph of capital P of x. So here we have the polynomial function q of x, which is equal to x minus 2 squared times x plus 1 cubed times 3x minus 8. And we're going to find our y-intercept by taking and plugging a 0 in for x. So we get y equals 0 minus 2 will be negative 2 squared times 0 plus 1 is 1 cubed times 3 times 0 is 0 minus 8. It'll just be negative 8. So that gives us 4 times 1 times negative 8. So we get a y-intercept of negative 32. If we're looking to put this into an ordered pair for a typical point notation, we would have a 0 for x and then our negative 32 for y. Right now for our x-intercepts, we put a 0 in for y and then solve for x, so we wind up with 0 equals x minus 2 squared times x plus 1 cubed times 3x minus 8. And since this polynomial is already given to us in factored form, we can just go ahead and set each one of these factors now then equal to 0. So we have the x minus 2 squared equals 0, the x plus 1 cubed equals 0, and a 3x minus 8 equals 0. And with the x minus 2 quantity squared, since it's just the same factor both times, we can just look at this as x minus 2 to be equal to 0. If you want, you can go ahead and write in it's a square root of both sides to make that more algebraically pleasing to you. It's not necessary, but it's fine if you feel the need to do it. In either event, that'll leave you with x minus 2 equals 0. So we add 2 to both sides to get x equals positive 2. And we're going to play the same sort of game here with the x plus 1 cubed being equal to 0. We're just going to focus on the x plus 1 and set it equal to 0. Again, you can write the cube root of both sides if you wish. And then to solve this guy, we subtract 1 from both sides to get x equals a negative 1. Now for the 3x minus 8 to equal 0, we start off by adding 8 to both sides. So we get 3x equals 8, then we'll divide out both sides by 3, and we get x is equal to 8/3. If we're going to look to find the multiplicity of each 0, and what we're going to do is just look at the exponents on each one of the factors that generated a 0 for us. So for the case of the x equals 2, we come back and look and say, okay, that came out of the x minus 2, which was squared. So that tells us the 0 of x equals 2 has a multiplicity of 2. Similarly then for the 0 of x equals negative 1, here we had a multiplicity of 3 based on the exponent that was on that factor. And then for the 0 of x equals 8/3, the exponent there is assumed to be a 1, so that tells us we had a multiplicity of 1 for that particular 0. When we look to find the degree, since this is in factored form for us, all we need to do is add up all of our multiplicities. So we have 2 plus 3 plus 1, which gives us a degree of 6. Now what our leading coefficient, and in this case that'll be whatever happens if we were to multiply out this whole polynomial. And so to do that, we'll kind of look at this as an inadvertent multiplication. But we're not going to multiply this thing all the way out. That would take far too long. So what we were starting with was x minus 2 squared, the x plus 1 cubed, and the 3x minus 8. So the way we're going to approach this is look and see what the biggest exponent variable term would be for each of these particular factors. So when we start with the x minus 2 quantity squared, if we were to multiply this out, that would give us something with an x squared, and then a bunch of other stuff that we don't really care about for the purposes of this particular exercise. So with the x plus 1 cubed, if we're going to look and multiply that guy out, it would contain an x to the third plus a bunch of other things. And then that 3x minus 8 is going to stay more or less the same. All right, so now if we take the x squared from that first set of parentheses and multiply it by the x cubed in the second set of parentheses, those two guys together would give us an x to the fifth, plus a bunch of other stuff that we would then multiply by the 3x minus 8. And so if we were to multiply those things together, we wind up with 3x to the sixth plus a bunch of other things. So that tells us then our leading coefficient then is going to be this number that was in front, which is our 3. So we have a positive 3 for our leading coefficient. Now we're going to take all of that information and kind of just shorthand it here. So for our y-intercept, we had the point 0 and negative 32. For our x-intercepts, or zeros, depending on how you feel like referring to them, those were 2, negative 1, and 8/3. Now remember, we also want to know the multiplicity of each one of those zeros. So with 2, that multiplicity was a positive 2. Actually, I don't really need to know that it's positive, but there it is. For the x equals negative 1, we had a multiplicity there of 3. And for the x equals 8/3, that had a multiplicity of 1. Now remember, the multiplicities are important for us to find because they will tell us what is happening with the graph at each zero. Then we found the degree by adding up all those multiplicities and discovered our degree was 6, and that our leading coefficient was a positive 3. And now, based on all the information we've got to the left, we're going to sketch a graph of our function q of x. So we're going to start off looking at our y-intercept, which is going to be at negative 32. So we're going to come down here, mark that as our negative 32. This isn't meant to be drawn to scale, and it would take forever if we were going to draw 32 hash marks out anyways. So we're just going to basically do a rough sketch that'll have all the relevant details of this graph in it. So we've got our y-intercept marked. So now we're going to go to our x-intercept. So we had one here at negative 1. And we had one at positive 2. The other was at 8/3, which will be just before positive 3. So we're going to call that our 8/3 here. All right, we're going to mark each one of these x-intercepts. All right, now that we've got that taken care of, we're going to use the degree and leading coefficient together to help us determine which direction we're going to go with our end behavior of this graph. With the degree of 6, and 6 is an even number, that tells us our graph is either going to start and end up, or, if the leading coefficient is negative, it's going to start and end down. Now, since we did discover our leading coefficient is a positive 3, we know we're going to start and end in the upward direction, so we'll just come on down here. Now, since since negative 1 here had a negative multiplicity, we're just going to cross through this graph, through the x-axis for the graph here, and keep on going until we get to our y-intercept at negative 32. Now, you can test various points beyond this to get a better shape of the graph. What's going to happen is we're going to keep going past 32, curl around, head back up to positive 2 here. Now, because positive 2 had an even multiplicity, we're only going to touch the graph, the x-axis here, and we're going to come back up towards the 8/3 and through, because again that was an odd multiplicity, and head back up the same way we came at the beginning. This is our complete graph of the polynomial q of x, and we're done. Here we're given the polynomial function h of x equals x to the 5th plus 9x cubed minus 8x squared minus 72. And we've been asked to factor h into linear and irreducible quadratic factors with real coefficients. So basically what that is going to tell us to do is just break this down as best we can without actually having to resort to complex numbers. On the face of it, this is kind of an ugly problem because we've got a 5th power, so that traditionally doesn't jump out and give you a lot of factoring options. Another irritating factor is that we've got 4 terms and there is absolutely no common factors to all 4 terms. So what we're going to do instead is switch over to try a grouping technique. So we're just going to look at the first 2 terms here as group 1 and the second 2 terms as group 2 and see if we can get anything to come out of it that way. So in group 1, we've got x to the 5th plus 9x cubed. So we would have a common factor here of x to the 3rd power, which will leave us with x squared plus 9. So if we're fortunate in group 2, we'll get the same thing. And in group 2, we have a common factor of a negative 8. We want it to be a negative 8 because we're trying to get this second group to match up to the x squared plus 9 that we got from the first group. And since both the x squared and the 9 are positive in the first group, then for the second group we need to factor out a negative to make what's left behind stay positive. And as luck would have it, we get an x squared plus 9 out of that guy as well. So that means that we have a new and improved common factor between these 2 groups of x squared plus 9. So we can pull that guy out to get x squared plus 9 times x cubed minus 8. Now, this has been factored a little bit, but this is not limited to strictly linear and irreducible quadratic factors. X squared plus 9 is irreducible and quadratic. However, x to the 3rd minus 8 is neither linear nor quadratic, so we have to keep going. And as it happens here, 8 is a perfect cube, so that means this x cubed minus 8 is in fact going to be broken down using a difference of 2 cubes. So we keep the x squared plus 9 along for the ride, and we use our difference of 2 cubes formula here to give us x minus 2 times x squared plus 2x plus 4. Alright, so here's our solution for breaking down h of x into linear and irreducible quadratic factors with real coefficients. And we're going to use that breakdown to help us with the second part of this question, which is to factor h of x into linear factors with complex coefficients. So to do that, we're going to start by leaving the x minus 2 alone and focus on the x squared plus 9. And what we're going to do is find out what happens when this guy is equal to 0. Now, we know it's going to involve complex numbers. The giveaway was in the instructions to factor this into linear factors with complex coefficients, and so we're going to see what happens when we set each of these two irreducible quadratic factors equal to 0. So with the x squared plus 9, this is going to get solved just as you would anything else, straight up algebraically. So we subtract the 9 over to the right side, so we've got x squared equals negative 9. And we're going to take the square root of both sides. So that'll leave us with an x on the left side. The square root of 9 is 3, and because it's negative, when we do that square root thing, we are going to have a 3i. Now, because what we took the square root of was something with a variable in it, we get a plus or minus to go with that 3i. So we've broken that guy down as far as we can, so that's going to give us our head start for the h of x. So we're going to leave the x minus 2 alone, as I mentioned before. And then we have an x minus 3i and an x plus 3i to go with that. But we still have this x squared x squared plus 2x plus 4 still to deal with. And so we're going to take and set him equal to 0 as well. Now there's no nice way of getting around this one. We're going to have to use the quadratic formula here. So what we're going to do is look and identify our a, b, and c right off the bat. So the x squared doesn't have anything written in front of it, so we're going to assume that's a 1 for our a. The positive 2 here, that's our b. And this plus 4 here is going to be our c. So what we've got here then is x equals the opposite of b, so that'll be a negative 2, plus or minus the square root of b squared, so 2 squared is 4, minus 4ac, so it's 4 times 1 times another 4, all over 2a. Oops, don't need to write a, I know what it is. It's 2 times 1. So that gives us negative 2 plus or minus the square root of 4 minus 4 times 1 times 4 is 16, all over 2. We get negative 2 plus or minus the square root of 4 minus 16 is a negative 12 over 2. So let's see, that'll break down into, let's see, 12 will be 4 times 3, so that'll give us a 2, and that was negative, so that'll be an I, the square root of 3, all over 2, and that will simplify out since there's this 2 in the denominator here. So that gives us an option of splitting this up. So we're going to call this, oops, I'll switch back to black. Negative 2 over 2 plus or minus 2i times the square root of 3 over 2, which is negative 1 plus or minus I times the square root of 3. So that's what we're going to have to carry on to finish up with our h of x, but I don't have enough room here, so we'll forget about this guy for the time being. And we'll try this again. Alright, so we had our h of x had the x minus 2, the x minus 3i, and the x plus 3i. And we have our x minus, and then our kind of less pleasant solution here of negative 1 plus I times the square root of 3, and x minus negative 1 minus I times the square root of 3 for our complete factorization of h of x into linear factors with complex coefficients. Alright, we've been given this rational function r of x, which equals x minus 3 times x plus 3 all over x minus 4 times x plus 1 quantity squared. And we're looking to find the x and y intercepts as well as any asymptotes of this function. And once we've found all that information, we've been asked to draw a sketch as well. So we'll start looking at the y-intercept. That's typically about the easiest to find. So we'll replace the r of x with a y. And we'll put a 0 in for x. So we get 0 minus 3 to be negative 3 times 0 plus 3 is 3 in the top. And then we wind up with 0 minus 4, so that's a negative 4. And 0 plus 1 is 1, even though it's squared. 4 are two factors in the denominator. And so that leaves us with 3 times negative 3 in the top, which will give us a negative 9, over negative 4 times 1, which is a negative 4. So this gives us a y-intercept of 9/4. Now if we're looking to put this as an ordered pair, obviously we put a 0 in for x, then 9/4. So now for our x-intercepts, we are just going to reverse the process we just did and put a 0 in for y. So that leaves us with x minus 3 times x plus 3 in the top over x minus 4 times x plus 1 squared in the bottom. And now the way we're going to handle this is just straight up algebraically, and most everyone hates the fractional component here, so we're going to take and multiply through by our denominator here of x minus 4x plus 1 squared to both sides, so that we can focus on just the numerator. Alright, now that we've done that, the left side is still 0, so we're multiplying by 0. And on the right side, we're left with x minus 3 times x plus 3. And so now we're just going to set each one of these two factors equal to 0 and solve for x. So with the x minus 3 equal to 0, we add 3 to both sides to get x equals positive 3. And with the x plus 3 equal to 0, we subtract 3 from both sides to get x equals negative 3. So these are our two x-intercepts. Next, what we're going to do is focus on finding any vertical asymptotes. And how we're going to do that is we're just going to take our denominator, and since there's nothing that's going to be simplified out, we take the entire denominator of our rational function and set it equal to 0. So that's x minus 4 times x plus 1 squared to be equal to 0. And we're going to set each one of these two factors equal to 0. So if x minus 4 is equal to 0, we add 4 to both sides to get x equals 4. I'm going to look at the x plus 1 is equal to 0. The fact that the quantity was being squared is irrelevant for our purposes here, but just so we don't get mixed up, I'll draw that little squiggly line. So if x plus 1 is equal to 0, we are going to subtract 1 from both sides, and we get x equals a negative 1. Now, when we were looking at the x-intercepts, we wrote x equals 3 and x equals negative 3, but we could have just as easily written those as ordered pairs. As here, that would have been the point 3, 0, and here would have had the point negative 3, 0. But for the vertical asymptotes, these guys are described as equations, so what we want is this entirety, x equals 4 and x equals negative 1, if we're going to use those to describe our vertical asymptotes. Alright, now I'm going to scroll on up here and rewrite our function r of x to be equal to x minus 3 times x plus 3 over x minus 4 x plus 1 squared, because we still have to look for a horizontal or a slant asymptote. Now the way we're going to make that determination is by just taking a look at the degree of the top part of our fraction and compare it to the degree of the bottom. In the numerator, If we were to multiply this all the way out, we would wind up having degree for the numerator here of 2 versus our denominator would have a degree versus our denominator, which would have a degree of 3. Now, since the degree of the numerator is less than the degree of the denominator, that tells us that we've got a horizontal asymptote. And furthermore, it tells us that that horizontal asymptote is going to be at the x-axis, which is the line y equals 0 for that horizontal asymptote. Just like the vertical asymptote, make sure you have the y equals component in there, because this is describing a line, not just a point, not just a value. So the y and the equals part needs to be there. And now we're going to draw a rough sketch of our rational function here, r of x. So we'll start with our y-intercept, which is at 9/4, so that's going to be just above 2. Here's our positive 9/4. Then we're going to look at our x-intercepts, which we're at 3 and negative 3. Alright, so we've got those two guys marked down. Now, let's go ahead and take a look at our vertical asymptotes. Those occurred when x was equal to negative 1, which you've already got here, and when x equaled a positive 4. Now, I've marked those two values on the x-axis, but remember, these are vertical lines. Now, we're not going to draw them solid because they are shaping the graph, but they are not a part of the graph. So we represent these guys as dotted lines. And I'll just make a note down here towards the bottom. This was our x equals negative 1. This is our x equals positive 4. And then lastly, what we've got here is our horizontal asymptote, which was the x-axis. So that's just right along here. Now, if you're at all concerned about the fact that the horizontal asymptote gets crossed at our x-intercepts at 3 and negative 3, please don't be. That is not a big deal. The horizontal asymptote is able to be crossed. It's just vertical asymptotes that cannot. So when we get down to drawing our graph, those x-intercepts, we know we're going to follow our horizontal asymptote for our extreme values. So that's the end of behavior. Extreme values of x, I should say. So from the negative x side of things, we're going to be following our horizontal asymptote. Then we're just going to sneak up here, cross through negative 3, and then follow up towards that vertical asymptote there at x equals negative 1. Now, on the other side of that asymptote, we're going to come down and sneak through at our y-intercept 9/4, and kind of snake around down through our x-intercept of positive 3, and keep heading down towards that vertical asymptote at x equals 4. And then finally what's going to happen is our graph is going to pick back up here at the top on the other side of that vertical asymptote, and then curl down towards the other end of the horizontal asymptote on the y-axis. And so that is our rough sketch of our function r of x. We've been given the rational function capital R of x, which is equal to 2x minus 1 times x plus 4 squared over x minus 2 times 3x minus 5 quantity squared. And we're going to be looking to find the intercepts, asymptotes, all of the relevant information that will allow us to then draw a sketch of this function capital R of x. We're going to start off by looking at our y-intercept. So we'll replace the capital R of x with a y, and we're going to put a 0 in for x. So that leaves us with a negative 1 times 4 squared over 2 times negative 5 squared. So 4 squared is 16 times a negative 1, gives us a negative 16 in the numerator. And 5 squared is 25 times 2 is 50 in the denominator, but these will actually simplify down because they both have a 2 in common, so that'll give us negative 8/25 for our y-intercept, which we're going to go ahead and sneak in here as the point 0 and negative 8/25. Alright, now we're going to find the x-intercepts. So we're going to take and put a 0 in for our y, and that gives us 0 equals 2x minus 1 times x plus 4 squared over x plus 2 times 3x minus 5 squared for our denominator. Now, the only part that really matters here is the numerator, but what we're going to do to justify that is we're just going to multiply out both sides by our denominator, x plus 2 times 3x minus 5 squared. All right, now this is more of a convenient algebraic shortcut. There's a more extensive mathy sort of explanation as to why we can do this, but for right now this should be sufficient. So the left side is still 0, so we're just multiplying by 0. On the right side, the x plus 2 and the 3x minus 5 squared cancel out, so we're left with 2x minus 1 times x plus 4, quantity squared. So with that being equal to 0, then we just need to take the 2x minus 1, set him equal to 0, and do the same thing with the x plus 4 squared. Equal to 0. So if the 2x minus 1 is equal to 0, we'll add 1 to both sides, so we get 2x equals 1, which gives us x equal to 1/2. And if the x plus 4 quantity squared is equal to 0, we can square root both sides just to get x plus 4 equals 0, and we'll subtract off 4 from both sides to get x equals negative 4. Now these can also be written as ordered pairs, so the first one would be 1/2 comma 0, and the second would be negative 4 comma 0, because these intercepts are points, so they'll have an x and a y coordinate. So now what we're going to do here is I'm going to scroll this up a little bit so we can now focus on the intercepts. We'll get the capital R of x rewritten here just for point of reference. So it's our 2x minus 1 times x plus 4 squared over our x plus 2 times 3x minus 5 squared. Alright, so next up is looking to find any vertical asymptotes. So now we're going to do that by just taking both parts of our denominator, since there were no simplifications possible, and set it equal to 0. So that gives us x plus 2 times 3x minus 5 quantity squared is equal to 0. So we'll set each factor equal to 0. So either x plus 2 equals 0, or the 3x minus 5 is equal to 0. If the x plus 2 is equal to 0, we subtract 2 from both sides to get x equals negative 2. If it's the 3x minus 5, we'll add 5 to both sides to get 3x equals 5. And then divide out both sides by 3 to get x equals 5/3. Now, with vertical asymptotes, it's important to remember that these are defining equations of lines. So for the vertical asymptote, we need to have both the x equals and the number there. So x equals 5/3 and x equals negative 2. The only thing that leaves us left to do is find any horizontal or slant asymptotes. Let's try that again. So all this leaves us to do is find any horizontal or slant asymptotes. Remember, we only get one or the other. We won't have both. All right, so the way we're going to make that determination is looking at the degree of the numerator and denominator of this rational function. So for the degree of the numerator, that would be 3 versus the degree of the denominator, which would be also 3. So now when the degree of the numerator is equal to the degree of the denominator, we wind up having a horizontal asymptote. But it is not the simple x-axis as it can be sometimes. That happens when the degree of the numerator is smaller than the degree of the denominator. When the degree of the numerator is equal to the degree of the denominator, then we have to actually look at our leading coefficients. So what would happen here is if we were to multiply the numerator all the way out, we would have this 2x minus 1 times x squared plus a bunch of other stuff. We don't really care about that because I'm just looking for the leading coefficients here. And similarly in the denominator we would have an x plus 2 times something with a 9x squared and a bunch of other stuff afterwards. So in the further simplification, if we were to distribute that 2x minus 1 all the way through that second quantity, we would wind up having 2x to the third plus a bunch of other stuff over 9x to the third plus a bunch of other stuff as well. And when the degree of the top of the rational function is equal to the degree of the bottom, we do the horizontal asymptote by just examining the leading coefficients, which in this case is going to be 2 and 9. And remember, we're describing a horizontal line, so that's going to be y equals and some number, in this case 2/9, whatever those coefficients, leading coefficients happen to be. So that is the equation for our horizontal asymptote. Remember, asymptotes are equations of lines, so you need to have the y equals part in there as well. Right, so now we've done all that we can, found all the relevant details, so we can start worrying about our sketch. So I'm going to rewrite all of the information we found here for our function capital R of x, which was equal to 2x minus 1 times x plus 4 squared over x plus 2 times 3x minus 5 squared. All right, so we found our y-intercept to be the point 0, negative 8/25. Found the x-intercepts to be negative 4, 0, and 1/2, 0. We found two vertical asymptotes at x equals negative 2 and x equals 5/3. And we found a horizontal asymptote at the line y equals 2/9. So with all of that information, what we're going to do is put it all together to draw a sketch of this graph. All right, so we're going to start with our y-intercept. Now, rather than try to get negative 8/25 on the money according to some sort of scale, I'm just going to say it's pretty close to the origin, not quite there. So this guy here is our negative 8/25. I'm going to play a similar game with our x-intercepts also. So we have negative 4 and our positive 1/2. So now that our intercepts are taken care of, now we're going to go ahead and start worrying about drawing in our asymptotes. So we'll start with our vertical asymptotes. So at negative 2, and then at positive 5/3. Alright, so we'll draw our vertical lines. Remember to make them dotted, because while they are lines, they are not a part of the graph officially. They just help shape the graph. And we're going to go ahead and label those as relevant pieces of our puzzle. So we have our x equals -2, and x equals 5/3. Then we have to do our horizontal asymptote, which is at positive 2/9. So we'll call that up here. And draw our dotted horizontal line there. Y equals 2/9. And then all that's left for us to do is kind of connect the dots. Right. Now, if you're wondering where all of these kind of connect the dots sorts of ideas come from, if you're uncertain on how the graph will be drawn from here, you can always take a look at plotting additional points to get a better sense of the shape, or you can punch this into a graphing calculator to verify that your shapes are correct for all of this. As it happens, what's going to be here is below the horizontal asymptote out towards -infinity for the x values. We're going to come down, oops, wrong color. Get rid of that guy. So we're going to come down, touch the -4 on the x-axis, then pop up towards our vertical asymptote. Then we're going to skip over and start down here at -infinity. On the other side of that, x equals -2, and kind of curve around in sort of a serpentine pattern here to hit the y and x intercepts. And then we can pop back over, and that x equals 5/3, and get the rest of our graph to kind of curl around and head out towards positive infinity, following the line y equals 2/9, but slightly above. And once all of those pieces are together, that is our graph for capital R of x. Here we're given the rational function q of x equals 4x squared minus 16x over 2x plus 8. And we're asked to find all the intercepts and any asymptotes and all relevant data that will allow us to sketch a graph of this particular rational function. So we'll start off looking at finding the y-intercept. So for the y-intercept, we're just going to put a 0 in for x. And so we'll plug a y here instead of the q of x, and we get 0 minus 0 over 0 plus 8. So we get 0 over 8, which is just 0. So our y-intercept is the origin. It's the point 0, 0. Right. Now we move on to the x-intercepts. So now we're going to put a 0 in for y and solve for the corresponding x values. So we get 0 equals 4x squared minus 16x over 2x plus 8. And now we're going to multiply both sides by 2x plus 8 so that we can just focus on the part that's really important, which is the numerator of our rational function. So we get 0 equals 4x squared minus 16x. Now to solve this, we're just going to do some basic algebra here. So we'll factor out the common factor of 4x. That'll leave us with x minus 4. So now we're going to set each factor with a variable in it equal to 0. So we get 4x equals 0, or x minus 4 equals 0. If it's the 4x that's equal to 0, we know x is equal to 0 when we divide both sides by 4. If it's the x minus 4 that's equal to 0, we add 4 to both sides to get x equals 4. And so these are going to be representing the points 0, 0, and 4, 0 for our x-intercepts. Alright, so we scrolled up here to focus on the next part of our rational function info finder, which is looking for the vertical asymptotes, but I want to rewrite the equation here first. So we get 4x squared minus 16 over 2x plus 8. All right, so when we look at the vertical asymptotes, what we want to do is just take our denominator and set it equal to 0. So we'll take our 2x plus 8, set him equal to 0, and just solve this algebraically. So we'll subtract off the 8. So we get 2x equals negative 8. Divide out both sides by 2 to get x equals negative 4. Now remember, this is for our vertical asymptote, and so that means we need to have an equation. So the whole x equals and negative 4 needs to be a part of that. And finally, what we're going to work on is determining if we have a horizontal or a slant asymptote. And the way we're going to do this is by comparing the degrees of the top and bottom. So we look at the degree of the numerator, which happens to be 2, and then we want the degree of the denominator, which is 1. And with the degree of the numerator being 1 larger than the degree of the denominator, this tells us that we are going to have a slant asymptote, which kind of is a, well, least desirable option of the two, because that puts us in for a little bit more work here. So in order to find the equation for our slant asymptote, we get to go through and do some polynomial long division. So we'll take our 2x plus 8 and divide that into the 4x squared minus 16x. The way we're going to continue on is just like regular long division. We have our 2x, and we want to turn him into our 4x squared, so we need to multiply by 2x. And we're going to distribute that 2x through to both parts, the 2x and the plus 8. So 2x times 2x is 4x squared, and then 2x times the 8 will give us a plus 16x, but just like all other divisions, we are going to subtract. So that changes our signs here to both negatives. So with the 4x squareds, those go away, but negative 16x minus another 16x gives us a negative 32x, and we'll treat this just like we would any other division problem. So we're out of x's, so we'll just consider that as 0, and we'll drop down the next term. And so we now want the 2x to turn into a negative 32x, so that means we need to multiply them by a negative 16, and once again we are going to multiply that through. So we get a negative 32x, then we get our 16 times 8 will give us a negative 128. And again, though, we're going to subtract, so both of these signs are now going to change to plus. The 32x's go away, and we're left with 128. Now, this would ordinarily go in the position of our remainder, but, and this is the kind of good news for dealing with slant asymptotes, we do not need the remainder for anything. We're going to ignore the remainder and just rewrite our slant asymptote. Again, this needs to be as an equation, so we have the y equals, then we're going to take our 2x minus 16, put it into place, and so that is our equation for our slant asymptote. Now what we're going to do is put all of those pieces together that we've found so that we can sketch a graph. And so we had our function here again, just as a reminder, was 4x squared minus 16 over 2x plus 8. We found a y-intercept of the origin, the point 0, 0, which is also an x-intercept. And we had another x-intercept at the point 4, 0. We found a vertical asymptote at the line x equals negative 4. and our slant asymptote, the line y equals 2x minus 16. Alright, so we're going to use that information to sketch a rough graph of q of x. And we will go ahead and start with our x and y intercepts. So here we have the origin, which is both an x and a y intercept. And we're going to come out here to positive 4 for another x-intercept. Now we'll worry about our vertical asymptote, so it'll be here at negative 4. In this particular graph, the scale is going to be a little bit bigger than you may have expected. You can always prepare for these things ahead of time before you start graphing by looking at the graphic calculator's image of the graph. That'll also help you verify where you've made any mistakes, if any. So here we have our vertical asymptote, x equals negative 4. And now we're going to draw our slant asymptote of 2x minus 16. So that's going to have a y-intercept kind of down in this neck of the woods here, negative 16. And 2x, positive slope, will have us moving up as we go from left to right. So now what we're going to focus on is just kind of sketching the rest of the graph. You can verify this again by looking at the graph produced by your graphing calculator, or you can plot various points that will help you flesh out the rest of the graph. What's going to happen is we're going to start down here at negative infinity, the x's, and kind of curl around before going back the way we came towards that vertical asymptote to the left of negative 4. We're going to come down from the right side here up towards positive infinity on our vertical asymptote and make our way through our x and y intercept because it's the origin, it's both, 0, and then turn down here in the fourth quadrant, go through x equals 4, then kind of follow our way back towards our slant asymptote. Alright, it's not the best picture I've ever drawn of a rough style of graph, but it gives you all the relevant information. We've been given this rational function, capital H of x, which is equal to 5x squared minus 80 over 4x squared minus 40x plus 96. We've been asked to find the intercepts as well as the location of any holes and all asymptotes for this particular rational function, and we're going to be sketching a graph of it. Because there's a possibility of being a hole in the graph, what we are going to do first is look to see what the most simplified form of this particular rational function will look like. So I'm going to factor out a 5 from the top, at least get me started. So that'll leave me with an x squared minus 16. And in our denominator, we've got a common factor of 4. So we can pull that guy out, which will leave us with an x squared minus 10x plus 24. Alright, now we're going to keep going with our factorizations. So we've got a difference of squares in the top. So it'll be an x minus 4 times an x plus 4 over 4. And let's see, for the x squared minus 10x plus 24, the 24 being positive means they're the same sign. The 10x is negative, so they're going to be both minuses. So with 24, that'll give us minus 6 minus 4. And as it happens, we have x minus 4s, both the top and the bottom. So we're going to cancel those guys out. Right, now we want to remember, though, that that was canceling themselves out, because that is going to come back later when we look for holes. So after that simplification, we're left with 5 times x plus 4 over 4 times x minus 6. Now, We found that. We'll go on to looking for x and y intercepts. Alright, so we'll do the y-intercepts first. So we put a 0 in for x, and that'll give us 5 times 4 here over 4 times a negative 6. And happen to spot our 4's canceling themselves out. So we're left with the y-intercept at negative 5/6, which is the point 0, negative 5/6. So we're going to look for any x-intercepts. So we'll take and set our simplified rational equation and set it equal to 0. So we get 0 equals 5 times x plus 4 over 4 times x minus 6. All we really care about is the numerator here, but we'll justify this by getting rid of the denominator by multiplying both sides by 4 times x minus 6. And so we're left with 0 equals 5 times x plus 4. Now, just divide out both sides by 5 to leave us with 0 equals x plus 4. And we'll subtract 4 from both sides to get x equals a negative 4. So that means for our x-intercept, we're at the point negative 4, 0. And at this point is when we're going to revisit that x minus 4 that we canceled out previously. Now it's not going to be a vertical asymptote, even though it did show up in the denominator. It's not going to be an x-intercept, even though it showed up in the numerator. But because they cancel themselves out, that's why we know that's going to be a hole in the graph. And it's generated by that x minus 4 factor that got canceled out. So if that were to be either an x-intercept or a vertical asymptote, we would take that x minus 4, set it equal to 0, which tells us we're going to have some sort of issue when x equals 4. So that hole happens when x equals 4, but we need to know what the corresponding y value is going to be. So we're going to take that and plug 4 into our simplified equation. So we have 5 times, this will be 4 plus 4 over 4 times 4 minus 6. So that gives us 5 times 8 in the top, 4 times a negative 2 in the bottom, which is a value of negative 5. So we did discover there's a hole in the graph at the point 4, negative 5. Now we're going to scroll that work on up and look for all the remaining features of our graph, namely the asymptotes, from our simplified version, which would be 5 over the x plus 4 over 4 times the x minus 6 for the simplified version. Alright, so now we will proceed by looking for any vertical asymptotes. So we'll take our denominator and set it equal to 0. Then we'll divide out both sides by 4, so we're left with x minus 6 equals 0. Add 6 to both sides, so we find our vertical asymptote occurs at the line x equals 6. Remember that for vertical asymptote, since it's describing an equation for a line, that x equals must be there. Alright, next up we're going to look to see if we have any horizontal or slant asymptotes. And to do that, we're going to examine the degree of both the top and the bottom of our simplified rational function here. So the degree of our numerator is 1, as is the degree of our denominator. So that tells us that we've got a horizontal asymptote. And we're going to find the equation by examining the leading coefficients of both the numerator and the denominator. So if we look at these two parts, 5 times x plus 4 over 4 times x minus 6. Since it's in a factored form already, the heavy lifting's already been done. Our leading coefficients of the top is 5. Leading coefficient of the bottom is 4. So for our horizontal asymptote here, we've got the line y equals 5/4. So now we're going to put all of these pieces together to generate a rough sketch of our graph for h of x. And I'm going to write it as it was in the original statement of the problem. So that's our 5x squared minus 80 over 4x squared minus 40x plus 96. The reason I'm doing that is to remind you that there was a hole in the graph that we need to remember to include. So we had our y-intercept here at 0.0 negative 5/6. We had our x-intercept at the point negative 4,0. We had our hole in the graph at the point 4, negative 5. We had a vertical asymptote, the line x equals 6. And we had a horizontal asymptote, the line y equals 5/4. Now we're going to put all of that together so we can generate a sketch of our graph. And we will start here with the y-intercept, as good a place as any. So that would be the 0.0 negative 5/6, which we're going to call right here. We had an x-intercept here at negative 4. We had vertical asymptote when x equals positive 6. So we'll just label that here so we can keep track of things. And our horizontal asymptote is at 5/4. So here's our line y equals 5/4. Now I haven't forgotten about the hole in the graph. I just wanted to get a rough idea of the sketch first. So what is going to happen here is we have a line coming here below the horizontal asymptote. It's going to creep down through negative 4 and then through 5/6. Now when we get to about where x equals 4 happens to be, that's where our hole is going to take place. Negative 5, before continuing on down to follow that vertical asymptote. But don't forget, there's still another part of the graph. We start up the top on the right side of our vertical asymptote and then swoop down to follow the horizontal asymptote for the very large positive values of x. So that's all the horizontal asymptote does, is dictate end behavior. And so this is our rough but complete sketch of this rational function capital H of x.